we're going to continue the series of Arthur X's, and I want to try to convince you in the contest of who had the most fun. So for us, I'll try to convince you I've had the most fun, but
a little higher, maybe. A little higher.
testing. Hello? Hello? No.
See if it's off.
It's all my one. So when you went to partial space flight center, you took he took hot spirits with a captain. And they both still working together there. Okay? So I'm going to try to do is convince you that I've had the most fun of anybody. I certainly have had the most calls. Which for boys means nothing. So I'm going to talk about, I was also the only one of this present students we're talking access here that was enlightened. I stayed enlightened. Can you hear me now? No. Think about it. Yeah. Testing. So I changed the title. I'm going to start off in space and we'll come down to ground after a while. So this is typical lighting you see when you look out your window here in Houston. This is what you see when you're above the top of the cloud. The light is released inside the cloud. It's hundreds of optical depths deep in the cloud, close to thousands of scatterings, and you see a puddle of light. This is what you need to detect in space. The challenge is during the daytime, sunlight shining on the top of the cloud is orders of magnitude brighter than the lightning source. So you have to do a series of processing techniques to be able to pour out very weak signal against a very bright factor. But we were successful in doing that. We launched our first sensor in 1995, an optical fence detector. We followed that up with a light imaging sensor launched on a trim satellite in 1997. It's still flying today. We're still collecting data today. So it's very stable. And the good news is, because of the success, in 2016, we're going to be launching another LIS in the same era on the space station. And in 2016, we finally gained the holy goal that my real mission for my career is to put a lightning sensor onto a geostationary satellite, onto those satellite operations. So starting in 2016, you guys will see it. On your daily weather forecast, you'll see my this in space. This is just showing a distribution. The first detailed measurement we have of the global distribution of lighting as a function of time and space. You notice as you go to the northern hemisphere summer, you suddenly start seeing the whole northern hemisphere light up as a function of heating. There are hypotheses that suggest that lightning is very sensitive to heating, and so a small increase in temperature could have a major increase in lightning flash rates. This is the same data set that's shown in local time. Notice how when the sun heats over the earth, everything is really dominated by air mass thunderstorms. The whole earth just lights up 1 heartbeat per day as the sun heats up here. Now, we do the universal time, it's just the way we process lightning across the earth. Well, we didn't realize that when we built this technology, we would actually be able to use it as a climatology sensor. We have 16 years now. Notice that the top shows the flashes per month as a function of time, and except for the jump in 2001, and that's when they raised the orbital altitudes of the spacecraft from 350 meters to 400 kilometers. That increased the field of view. We started seeing more lightning because of the larger field of view. But the response has been actually flat over this period of time, which is pretty well agreement where the temperature measurements have been flat also. So there's been basically no change in the amount of lightning activity on a global basis in the time the one days that we have. We can look at the, actually can see effects of the Southern anomaly, because when you fly through it, we get hit by electrons on our CCD, and they look at those events, and we can remove them by our processing techniques. So you can see that during the sunspot cycle, when it got quiet, you see we saw a lot more events, but when you filtered out the false events, response to the instrument was flat. And we did actually vicarious calibration of the instrument over a period of time by using light reflecting the top of high altitude clouds. Then the instrument response hasn't changed to about less than 1% over a period of time. So it's a very, very stable instrument. It's actually quite useful as a climatology instrument as well as looking for severe weather. This is what the new instrument's going to look like. The geostationary lightning mapper. It's being built right now. It's just going through calibration. All of this. The entrance aperture is 11 centimeters in diameter. You have to expand that to an 18 centimeter column space in order to accommodate an 8-degree field of view instrument. The narrowband filter, 1 nanometer wide, can only accommodate 5 degrees, so we expand it up so we can get right through and thus cover the full disk area. This instrument processes almost 10 to the 9 pixels per second with 14 bits resolution. It has 56 parallel processors, or pipeline parallel processors, to be able to process that kind of data set. And then it basically converts images to events and transfers data down. And the reason we were able to actually sell this as an operational instrument on GOES is because of the relationship between severe weather and lightning. This is an example of a case in Florida. The top panel is total lightning, bottom panel is radar. Notice this jump signature here. When the cloud starts to intensify, the updraft intensifies, you get more charge generation, the lightning flash rate increases dramatically. And then as the cloud starts to downdraft forms, the funnel starts going down, you basically have a tornado on the ground. This typical lead time is when you first see the jump signature to the tornado on the ground is in excess of 20 minutes. Present time, warning time, the National Weather Service has with radar is around 12 minutes. So it's a major increase in warning that the lightning map will bring to the community. Plus an increase in better warning time and lower false alarm. So this is the real discovery that we made that really convinced Noah to pour a lot of money into building the sensor. So that's all I'm going to talk about on space-based lightning. But I want to talk about some high-speed lightning spectroscopy. Back in the 60s, there was a lot of work done into spectroscopy using film systems. But they were very limited because it's very hard to get, they're very nonlinear, it's hard to get quantitative measurements, and you can only go so fast. But with modern cameras, we're able to actually do very high speed lightning spectroscopy. I mean, we put together a system that allows us to make 1 million spectra per second of lightning, which is about as fast, it's almost fast enough, but not quite. So this is some of the things we're trying to do. We really don't have enough accurate information to properly model the lightning channel. So we try to develop a sub-microsecond spectrometer, and we look at the luminosity, temperatures, electron densities, activities, and electric fields. I'll show you some spectrum. We do this on triggered lightning. This is an example of a rocket triggered lightning flash. Notice the green here. That's the copper wire that brings the lightning down to where we want it. At the base, we're able to measure the current, so we know what the energy input is. We can measure the luminosity. We put our spectrometer, usually we put someone around here. We can shoot higher up there, as you can see, so we can do a spectrum of natural lightning. This is what it looks like when you get a lot of copper in it. This is a natural lightning spectrum. You can see some of the emission lines. This was taken when I first started to do this. I borrowed a spectrometer from Steve Mindy, and then we designed our own and built it, and I had it built. And these are the two of the new spectrometers that we had built. This shows the high-speed cameras. These are large prisms. Believe it or not, both those spectrometers are looking at exactly the same spot for the lightning. This one has such high dispersion that we actually have to see lightning from there. You have to look this way. I'll show you the results from that. That's not H alpha spectrometer. This is just a couple of examples of spectrum. You can see the wavelengths there. This is the separator coming down. This is the this is when the peak current is occurring. Notice the kind of resolution we're getting. These are each 1.5 microsecond spectrum. This is then the next one, and after that it's already starting to come down. So within a few microseconds, the optical emissions have peaked, and it's descending. And this is the subtraction of the first one from the second one. Notice these lines. Those are doubly ionized nitrogen lines. The first time doubly ionized nitrogen has been detected. Because they last only the first frame. So if you subtract the 2 frames, you see the doubly ionized. The rest of the ones are single ionized nitrogen lines. And this shows that at the time, the temperatures associated with that are well over 40,000 degrees C. The doubly ionized line. And notice that by the next frame, you're down to the 30s, and almost all the doubly ionized lines are gone. Notice here this is the red line. The red line is current. The black line is temperature of the channel, lighting channel, the ionized channel. Notice don't worry about the first part where we actually need a little bit of time resolution. You notice how rapidly the temperature's falling off compared to the current. That is partially fused expansion of the channel. Energy is going into the expansion of the channel, making it stronger. By the time that's finished, they basically track each other very nicely. So this is the first measurement also of actually seeing the time history of the channel expansion. And this shows you the emissions, the atomic emissions that we're seeing. The first frame, you see doubly ionized nitrogen, and then you can see the time history of the singly ionized nitrogen, and then the neutrals start taking over and last for quite a while. But even the C line, it cools off fast enough during the channel expansion, and after about 10 microseconds, most of the ionized emission lines are over in the space. You start seeing all the neutrals. This just gives you a longer history, and the whole channel stays hot for milliseconds actually, and that's why they would get subsequent return strokes and actually have light come down the same channel again. This shows you the luminosity profile. You see the same thing. The luminosity falls off more rapidly than the current does, again, because the channel's expanding initially. Once that channel expansion is over, they basically tend to track each other. So we're getting the parameters we need to properly model the plasma channel now. This is a specialized H alpha spectrometer. This is just the H alpha line. You see we have about half an inch from resolution. These are 1 million spectra per second data. You can go back again, and notice how wide it is at the beginning. Very, very wide. H alpha is the width of the H alpha line is being used to measure pressure volume to try to calculate what the electron density in light channel from. So it's always assumed that that's simple pressure volume. As you saw from the first line there, it's much wider than we expect if you look at it in a very short time, the first few microseconds. So we look, it can be various causes of volume. Okay, go on. Anyway, what we're thinking is that it's not just pressure volume due to the internal stark effect, but when you have connectivity of the channel and you bring it up the ground, you basically have charge in the corona sheath around it. You're going to have an actual electric field, which can be on the order of no more than 1 million volts per meter. You think that's initially causing extra volume and it's causing the lighting. So you see, as time goes on, you start a single pressure volume would be fitted by a single Lorentzian. You can see we start fitting a single Lorentzian as time goes on. Okay. Hugh started off doing acoustic reconstruction to find out where the lighting channel was. We take that technology and added electronics and GPS. We can track we use field changing networks now to track where the light is. Probably the same technique that Arthur did with acoustics. So what you see here is a typical cloud ground stroke, cloud ground flash. These are return strokes. And here are the locations of the charge centers that result in. So you can use the high frequency component, the radiation field of the electric field, to locate in space where that pulse came from. And we can use then the electrostatic chain to locate where the actual amount of charge is. So we can get energetics of the system. So just a continuation of this work. This is what the channel looks like. This is cloud ground. This is a picture of a intercloud flash. Notice the slow electrostatic field changes. Animation of it. You can see the radar picture up there, and you can see how the channel, this is the upper negative, upper positive, and down here is the lower negative charge. You can actually see the different charge regions. You can actually map out this and calculate what the, using the model, you can calculate how much charge is deposited along the channel as it breaks down. So, a lot of technology let us continue in the amount of time. So, I've got one more thing to do. And I'm going to talk about balloons. This is the old balloon, base balloon. That's Mark Webber fixing it up. This is a picture of this. Is what I did for my PhD. Measured that. We did the first electric field measurements inside thunderstorms with it. And at the model, thermostat got in. And but never got in because of the way the eddy flow around, never got area. So Mike Stewart, who works with me now, I'm not artist, thank God. Was that inspiration? He moved that thermostat to the spin panels so they get an accurate temperature. And in the process, he invented balloon triggered lightning. This is a patent after it was in a lightning flash. Well, balloon triggered lightning actually has some value, so we modified it. For a while, we decided that high pressure air to shoot up very rapidly and trigger. And there's some really good things you can do with that. First of all, you measure your electric field, and right now there's no understanding of what the how strong electric field is necessary to propagate a streamer. A leader. Very important because rockets get launched and they can trigger lightning. So we actually understand the electric field necessary for leader propagation. We can actually write better rules to protect rockets. The second thing we're going to do is this July, we're going down to the Panama Canal, and we're going to trigger lightning to specific trees because it's biologists to know the effect of lightning on tropical trees and their insect populations. So, we call that Holy Spirit.